Hopefully you've been following along up until this point. If not, I strongly encourage you to do so. Go to the Lean4 web and follow along in your browser, if you don't want to install it or whatever, or if you're on a different computer. That's by far the most convenient way to do it. But yeah, super important. You got to build up that muscle memory. This will be the last few episodes before we will start transitioning into more intermediate level lean, which I'm excited to do so. We've been limiting ourselves to hardly ever using even simp, just so that we get a feel for the lemmas and especially for building proofs with functions and functional programming. But as we'll see later on, real world lean, well, you definitely need to know how to do that, but much more common is to use these more powerful tactics that we'll get to in MathLib. Last thing I want to say, just for this intro, definitely if you have any questions about anything in the videos, please comment. I'll do my best to answer them. And if you want a real lean programmer's point of view, definitely stay active in the Zulip. There's a lot of people who are super helpful. So I strongly recommend that too. All right, let's get into it. All right, so we left off with equality and using rewrite with and have statements with to do equational reasoning, and along with calc to do reasoning on expressions. So I think I covered calc enough. So I'm just going to go ahead and move on to the existential quantifier. All you got to know in lean is just two things, right? It's the what would technically probably be called a witness and a hypothesis. So in this case, for example, the hypothesis is 1 is greater than 0, and you can create an exist statement that says there exists x such that that x is greater than 0, and you can do this just by giving those two things to the constructor, and then this can be, of course, used with an implicit constructor. So the square, not sure what you got, square angle brackets, angle brackets, which you can type with backslash less than or greater than. These come into play again with anonymous constructor notation, and as well as pattern matching. Of course, if you can, if they're a constructor, they can be pattern matched. And as you'll see in later examples, they do. Let's see, let's find some. Yeah, so here, this would be an example probably. Yep, so here's H, and they're pattern matching on the X and PX and QX. So that's why there's in the second hypothesis here that's being deconstructed is this expression, and so they're taking the right and left of it, which you would expect to do with an and. Okay, so you guys can definitely read this. Ooh, they're talking about the Curry-Howard isomorphism. I definitely need to cover that. It's my favorite thing. This allows us to co-opt this mechanism for writing proofs as well. So, oh, they're just talking about match. Okay, weird way to say this because it doesn't really make sense why that's related. But okay, cool mention. I will never knock them for mentioning that. All right, so let's go on to the exercises. So I'm just going to do all of these. I've already started with a couple of them just to make sure that I'm not going too slow. They have the answers, and I guess I'll just start by saying like they're once again doing things in a very functional lambda oriented kind of way. Lean supports two modes, basically tactic mode and exact or term mode, and I'm pretty much going to stick to mostly tactic mode for these just because it reads more like an imperative program, which I'm sure is more familiar to most of us. At least it was for me. I'm going to go ahead and start by explaining this proof super quick. I commented it pretty well, so you should be able to figure it out. Step through it by doing this with your keyboard. Put your cursor on the first line. So we have two cases for this constructor. The if and only if has modus ponens and modus ponens reversed. In the first case, we're going to assume there exists and a for all, and we're going to have to show R. And we're going to do that by pattern matching. We are pattern matching the exist statement. So we can deconstruct the exists x, p of x implies r into an x and a p of x implies r. And then we just specialize the for all with x and apply p of x. So that should be pretty clear to you. The second one requires a proof by contradiction. And I'm almost certain it does require classical logic here because I think the book even mentions it. We're trying to go from right to left. So we're starting with a for all in a implication, and we're trying to prove an exists. So if you are starting with a for all, remember that for alls are basically functions. And if you're just starting with a function or an implication, it's very difficult to do anything with that, right? Because what are you going to do with a function if you can't apply it to anything? So after we introduce our for all statement, we have as a hypothesis, as an argument to this function, the entire for all statement. So if we're going to use f of a to show r, we have to have this, and we don't have enough hypotheses to show this, right? Because you cannot create p of x. The p of x is, if you think about the for all as a function from x to p of x, then how are you going to create this? So instead we'll do a proof by contradiction. So when I'm here, I have to prove an exist statement. We will apply by contradiction to get something we can introduce. So we're going to assume this with intro nex. We're going to call that nex. And then at this point, we get to a place where we could literally finish the proof with simple. Instead of doing that, I go on, and you can explore this on your own. It's interesting. We use this for all const, which I also implemented myself just for demonstration purposes, which uses a non-empty, which is basically a different way of saying there exists. So definitely check this out. But I'm not going to cover the rest. Instead, we're just going to jump into the first ones. Oh, I also did this one. Shoot, I have to explain this too really quick. Maybe I should have started with a simpler one. Oh well, too late. There's no such thing as editing. We're going to, for this one, we're just proving the if and only if between a double negation inside an exist statement. Constructor, get your two cases, introduce the for all, deconstruct the exists. So once again, we're going in the left to right, then it's really easy because we get to assume this, we get to assume this, and then we just have to show false. So you show false by specializing the for all using the x that you had from the exists, and that gives you p of x, which, well, you have not p of x, so contradiction. Okay, and then we have intro exa. This one, we get to assume, oh, this is not a good name. This is a not ex. There does not exist. And so after we assume there does not exist p of x, then we can say, let's see, contradiction. We need a contradiction here because we have p of a in the goal. We have a non-exist statement. So what will we do with that? Yeah, you need a not p of a, and there's a p of a in the goal. You need a proof by contradiction. Okay, so finally we'll get to you get to actually watch me struggle through one of these. We're going to obtain, our intro. Our intro, when you're doing it without previously declared hypotheses, and obtain if you have a hypothesis already. So we're going to introduce x. We're going to introduce r. And that's it. And now we have to show r. So we just do that with the exact r. And we're done. Okay, and now I'm getting unused variable x. Interesting that I get the unused variable after I complete that makes a lot of sense. Okay, we'll give it an underscore so it stops complaining. So let's see what we have on this one. Goal, we get to introduce r. I should be using, because of course we don't want to confuse a with alpha. So we introduce r, type r, hr of type r, and we have to show there exists x such that r. We don't have, oh no, we do have an a. So yeah, so this is important. So this a of type alpha on the left side of this colon is the type of the example. So basically what you're proving is this, and what you're assuming is this on the left side. So we're assuming there is an a of type alpha. That is just another way of saying there exists. It's just that this is so if you want to prove this, right? If this were a theorem and we were calling it as applying it as a function or something, you would have to give an a of type alpha, and then you would have to give an r. So in other words, this is all exactly the same as this, no different, right? These two things are isomorphic, but we'll stick with the original proof and we'll say intro hr. And then it's a little bit convoluted because when we're looking at the goal, we don't really know what the type of x is, but we can recall that it's, or mouse over it in the goal and know that it's of type alpha. And we have something of type alpha. So we can create our exist statement with either angle brackets, or we could just use the actual constructor. So I'll do that. And we have exist a and hr. And that satisfies it because a is of type x, x is of type alpha. So if we give an a, that's what you could call an instance or a witness of alpha, and HR is, well, R. So give this an underscore. Okay, next one. Now we have an if and only if. I prefer doing if and only if with a constructor with 2 cases. And I'm not going to name the cases. They're modus ponens reverse, MP, MPR. So in other words, I could say case MP goes to, but I'm not going to do that. I'm just going to call it a dot. And in this case, we're going to be assuming there exists X, P of X, and R. So I'm going to do a double pattern match here to get the X, and then I'm going to pattern match again to get the each part of the and, because we'll definitely need those separately. I'm going to say HX, P of X, and HR. I forgot one. Okay. So, oops, I forgot the R intro. We're going to R intro this, and now we have to show an and. Yeah, we have to show an and. So we have to build the exists first. So here, now I could say, okay, there's a couple ways to do this, to approach this, right? I think the most idiomatic way to do this proof would be, assuming these were like more non-trivial, you want to break down your proof into parts, right? So we know R, we know HR, and if we're having trouble like reasoning about this, like if it's kind of filled up the stack space in your head, right? I mean, obviously this is pretty simple, but we can simplify, what we're doing before we try to tackle the full goal by saying it suffices to show, right? So we can say, well, since we know R, it suffices to show the left-hand side of this and by basically saying by suffices and.intro with the left-hand side unknown, right? So the way to do that is refine and.intro with h of R on the right side. And what happens is refine, when you give refine a placeholder like this, a synthetic hole, I should say, technically not exactly a placeholder, it's a synthetic placeholder. Refine will create a new goal that satisfies that placeholder, right? So for this case, it's going to create a goal that is the left side of the and, which is exists P of X, which is what we want. And in the right-hand side of the and, we actually just give HR, so no new goals will be created. Okay, so after this, all we have to show is there exists. Just for demonstration purposes, right? We can actually apply the same thing we just did with exists.intro. We can say, refine exists.intro. And let's just give, let's just put holes in both. Now we have 2 goals. Right? In the first goal, we have to show alpha, and in the second goal, we have to show, and now we have a little problem, right? We don't know exactly what the type hole is, the type of the hole is supposed to be. Well, I mean, if you think about this, it makes sense, right? Like if you have a proof of P of HX for some specific hypothesis of X, and you need to show that there exists at least one X that satisfies this condition, we should be able to use this somehow, right? So I should be able to say P of X here, and it should work. But we get a type mismatch because this type, P of HX, is not the same as, and I think it's because we have to use, it's a little bit confusing. We have to use whatever we use on the left side here. Okay, let's not try to be too fancy here. Yeah, so I should just be able to say exact. I think I'm overthinking this, exact, and then HX and PX. Yeah, as usual, I'm overthinking things. So this is a good lesson though. I mean, a good teaching opportunity. P of X is the right-hand side of an exist statement is bound to the left-hand side, right? Like what value you choose, what variable you choose on the left. If you say there exists X, well, it doesn't make sense to have the right side proposition not, be specific to that X. So what that means here is that you don't get to just give an arbitrary proof of anything of type X. It has to be the X that you said that there exists. So that's why I got that weird type error that said, well, this is not the same type, even though it said X, it said there exists X and there exists, sorry, no, it said PX and P of HX weren't the same. And they're not, because P of HX is not this, it's a specific one. It's not the same thing here. Unless we make it unless we, make an exist statement using it. So that's why refine didn't work unless we specified the HX. So let me actually just make sure that that's true. we were trying to do refine with exists.intro. Oh, of course, now it doesn't complain. I swear to God, it was complaining earlier about using exist.intro here. What's the problem? What's the difference? Let's go back. Maybe I was using apply. Oh no, I was specializing it to p of x, right? Yeah, so it's funny. It's funny that refine breaks when you make it closer to the answer, right? Because obviously, like, the answer is h of x, right? But if you add one hole, refine says, wait a minute, you can't say p of h of x has the same type as p of the type of the whole, right? Because the exist statement takes this, this on the left side, there exists x. That x better be in the right side equation, that exact same x, right? Not some arbitrary x like in p of x. hx is of type alpha, just like x, but we need the specific one for the exist. So the specifying the specific hx and a type hole would also not result in an error, because obviously the h of x value doesn't depend on this type hole, but not the case in vice versa. And so if we did kind of the same idea as what I was originally going for up here, then all we would need to show is p of h of x, which is, by assumption. But this is just extra work, and you should try to use exact when you can, especially when it's super obvious like this. So we'll use exact instead of refine. Okay, next one. Next one should go faster because that one took our intro. Exists hx. We get to assume. Why am I assuming all these things? I think we only get to assume there exists x, p of x, and r. So the r is in the. So we have the nested pattern match is going to be for the exist statement, p of x, hr, and that's it. Okay. Now we have to make a proof of there exists x such that p of x and r. And the and is inside the exist statement this time. So up here, it's outside, and then down here, we need to put it inside. Okay, well, we know how to do that. You might recall from some of the earlier proofs we did with and, we had an R intro, and then we did like a fancy pattern match like this. And then when we just rearranged those bound variables in an anonymous constructor, we could rebuild the and with different orders or different nestings, different associativities. And that's all we have to do here, because Lean knows it's really unreadable when you do anonymous constructor stuff, because the exists and the and have the same kind of constructor notation, right? They both take two values. You can build them both with angle braces. I really need to figure out what I'm going to call those. Angle bracket, I don't know, whatever. So we're going to have something very similar here, right? We're going to have hx, and then instead of having the angles over on the left, they're going to be nested on the right, of x, right? And this is, there's definitely something deeper here, logically speaking, about the relationship between exists and. They're both tuples, and that's not a coincidence. It's just that their exists is like a tuple of a value and a proposition, whereas and is just two propositions, of course. Okay, but I don't like this. It's too implicit for my taste. So I'm going to put a comment up here. We'll call this the more explicit version. Should I say it's rated R? That's a bad joke for you. So instead of R intro, we're going to say, I believe we can probably do one of these with R intro, but then we'll probably have to change it to R cases. So I'm going to say exists, and we got to put it all in parentheses. But unfortunately, it still doesn't work. Now, if we're going to do our cases, then we are going to need to, I believe we'll need to introduce our pattern here. Our hypothesis. Let's just call it H. Do our cases H with pattern, unexpected syntax. Okay, what's unexpected about this? I'm just really not liking the angle braces, huh? Okay, let's use parentheses then. And eventually using. Oh boy. Oh, come on. Doesn't work. Have saved the day.